So we have seen that we have a hyperparameter which is lambda in our formulation of logistic regression, right? So if lambda equals to 0, we have the problem of overfitting as we saw earlier. And if you have lambda equals to infinity, we have the problem of underfitting, right? So now the question here is, the big question here is how to determine the best lambda, how to determine or how to find the best lambda, right? That's a question. So remember lambda here. So lambda in logistic regression is same like k in k nearest neighbor, right? Because k is also related to overfitting and underfitting, right? Right? So k is the hyperparameter. So all these are hyperparameters. So lambda is the hyperparameter in logistic regression, k is the hyperparameter in k nearest neighbor, and alpha is a hyperparameter in naive Bayes, where alpha is basically related with the with Laplace smoothing, right? With Laplace smoothing, right? So now how did we determine the right k and right alpha in the cases of k nearest neighbor and naive Bayes? So we said we'll draw a plot like this where k equals to 1, k equals to 2, k equals to 3, k equals to 4, so on. And we'll probably plot error. We can either plot error here or we can plot some performance measure like accuracy, AUC, log loss, whatever we want to use, right? And for each value of k, this error is basically the cross-validation error, to be very precise here. This is the cross-validation error or the cross-validation performance, either k-fold or simple cross-validation. So what happens? We would actually find some plot like this. And what we would say the k with the smallest cross-validation is the one that we will pick. That's how we determined. So we used cross-validation error. We used cross-validation error as the way to pick the best k. In this case, the best k would be 4. That's how we did all hyperparameter search or hyperparameter optimization in the case of k nearest neighbor, right? So hyperparameter search or optimization are basically tricks and techniques which will help us find hyperparameters. Now there is one problem with logistic regression. K in k nearest neighbor is an integer, right? Is an integer. It can take values like 1, 2, 3, etc. right? Up to n. But lambda in logistic regression is a real value, is a real number, is a real number. So the number of possible values of lambda are infinity, right? Because lambda belongs to real values. Lambda can take values like 0.1234. Lambda can take values like 0.2386. It can take them. There are infinitely many points that values that lambda can take. Right now, how do we find the right lambda? Is there a way to find the right lambda? Right. One trick in the literature of machine learning or in the literature of hyperparameter search and optimization. By the way, this is one of the big areas in machine learning. There is a lot of research in this area, right? So one technique to find lambda is called grid search. One technique is called grid search. The way it works is as follows. It's not very, very complex. It's basically sort of like a brute force technique. You can think of it as a brute force technique, right? The way it works is this. The way it works is I will take for various values of lambda, I will plot my cross-validation error. Remember, this is not test error. This is cross-validation error, right? But now, because there are infinitely many lambdas, there are many, many values of lambda, right? I can't search all of them. So what I'll do here, typically, this is what people do. People take a limited set of numbers. People say, let's test lambda equals to 0.001 first. Then let's test lambda equals to 0.01. So remember, this is 10 times this. This is 10 times this value. Then they'll say, let's test lambda equals to 0.1, right? So we will try and test multiple values of lambda here. Then we'll test lambda equals to 1, 10, 100, 1000, so on and so forth. Remember, I'm checking for various values of lambda which are multiples of 10 of each other, right? This is like a brute force search, right? So what am I doing? So this is one way that people typically employ. Remember, this is not a proper hardcore algorithm. This is like a heuristic. Grid search is like a heuristic. Other people could say, no, I don't want to search in this wide window, right? So people will say, I don't want to search between 0.001 to 1000. I will want to search in a much limited range. right? 6, 7, 8, 9, 10. So this is very much like the k nearest neighbor, the way we did for k nearest neighbor, except that typically in practice, people take values like this to explore the bunch of lambdas. So they'll take lambda which is very small, let's say 0.001, then they'll take lambda which is 0.01, and they'll find what is a cross-validation error for each of these values of lambda. Right? Similarly, they'll take lambda equals to 0.1, lambda equals to 1, lambda equals to 10, lambda equals to 100. For all these values, it'll plot. For example, suppose we get a plot like this. Then we know that lambda equals to 1. If the plot looks like this, it need not look like this, by the way. So if the plot looks like this, I know that, okay, roughly around lambda equals to 1, the value will be good. Right? So by multiplying these values by 10 every time, I'm searching a much larger space of possibilities, right? Because this is a linear space, right? Here I'm checking every value. Here this is a logarithmic space because I'm multiplying everything with 10. Right? Instead of adding, I'm multiplying here. So what lot of people do is they actually search lambda values in a very wide window between 1e minus 4 is nothing but 10 power minus 4. So what people typically do is people check in a very wide window between 10 power minus 4, 10 power minus 3, 10 power minus 2, 10 power minus 1, 10 power 0 is 1, 10, 10 square, 10 cube, and 10 power 4. This is typically what people will employ. And let's assume around 10 point, around this, suppose we get a very good value, they'll say, okay, of course, the right value could be 2.2 into 10 power minus 2, but that's okay. We'll not go into that detail. As long as we got the rough scale right, we are cool. Right? Remember, grid search is a brute force technique. Right? It's a purely brute force technique. There is no way. It's not a very smart technique. It's a very, very brute force technique. Because there is no system. This is the only, see, in k nearest neighbor, what did we do? We searched 1, 2, 3, 4, etc. In logistic regression, since the range is much larger, I'm doing 10 power minus 4, 10 power minus 3, 10 power minus 2, etc. Right? Now, instead of simple logistic regression, let's assume we had elastic net. You remember elastic net, right? Elastic net has this regularization, which is lambda 1 times L1 norm plus lambda 2 times L2 norm square. We had this, right? So here we had two hyperparameters, lambda 1 and lambda 2. Now, how do I find best here I have two hyperplanes, right? Two hyperparameters. In the earlier case, I had only one. What do I do when I have two hyperparameters? What is the strategy? What I do is simply this. I take values of lambda 1. I also take values of lambda 2. And I'll measure my error, my cross-validation error, as I change lambda 1 and lambda 2. And lambda 1, I'll take values from 10 power minus 3. Let's say I'm taking these values. 10 power 0, 10 power 1, 10 power 2, and 10 power 3. Right? Similarly, let's assume lambda 2 also I'm taking values between this up to 10 power 3. Right? Then for every pair of combinations, so what I'll do here is first I'll check when lambda 1 is 10 power minus 3 and lambda 2 is 10 power minus 3. Right? What is the value? Right? Next I'll check when lambda 1 is 10 power minus 2 and lambda 2 is 10 power minus 2. What is the value that I get? Right? Similarly, when lambda equals to 10 power minus 1 and lambda 2 equals to 10 power minus 1, what is the value? Right? So basically, I'm searching in this grid. If you think about it, this is like a grid that I'm searching in. Right? The first value is 10 power, lambda 1 equals to 10 power minus 3. Here also 10 power minus 3. This is 10 power minus 2. This is 10 power minus 2. This is 10 power minus 1. This is 10 power minus 1. This is 1. This is 1. So at every intersection in this grid here, right? At every intersection in this grid here, I'm trying to evaluate what is the cross-validation error if lambda 1 equals to this and lambda 2 equals to this. Right? So I look at all the possibilities. Suppose if there are let's say M1 possibilities here and if there are M2 possibilities here, I have to evaluate M1 into M2 possibilities. Which means, remember, when I say I have to evaluate these many times, I have to train my algorithm those many times with different values of lambda 1 and lambda 2 and compute the cross-validation error. Sometimes it's not going to be easy, right? Because there's so many this is called grid search because you're searching in a grid of possibilities, right? So the big problem with grid search is this. With grid search, it's called grid search because of this grid-like pattern that you'll see when you have more than one hyperparameter. The big problem with grid search is, imagine when we had lambda 1 parameter, when we had only one hyperparameter, when we had only one hyperparameter, when we had one hyperparameter, right? And let's assume we are looking at, let's say, M1 possibilities. The number of possibilities we have to try, the number of times we have to train and compute cross-validation error is M1 times. M1 times you need to train and compute cross-validation error, right? If you have two hyperparameters, lambda 1 and lambda 2, if you have two hyperparameters, then you have to do M1 times M2. You have to train M1 times M2. If you have, let's say, lambda 3, right? Then you have to train M1 into M2 into M3 times. Now, as the number of hyperparameters increase, right? The number of times the model needs to be trained, right? Increases exponentially, right? Look at it. If M1, M2, all of them are equal to M. Let's say if M1 equal to M2 equals to M3 equals to all of them are equal to M, then what is this? This is M power 1, this is M square, this is M cube, right? And if you have, let's say, K hyperparameters, what do you have? You have M power K times that you have to train the algorithm and test. And hence, as the number of hyperparameters increase, hence this is important. As the number of hyperparameters increase, right, which means as K increases, right, M power K increases exponentially, right, obviously. So hence grid search is not good when there are a lot of hyperparameters. In logistic regression, we typically do not have more than two hyperparameters, but we will see in deep learning, cases in deep learning where we have tens of hyperparameters. There are even cases where you have hundreds of hyperparameters for very large networks, right? So for very complex models, you'll see cases where you have not two, but tens, even hundreds of hyperparameters. So for that reason, there is another technique, an alternative to grid search called random search. And as the name suggests, it does exactly that. So suppose if I want to do random search on one hyperparameter lambda, suppose if I have only one hyperparameter lambda, and if I want to do random search on this, I will say that these values will lie between 10 power minus 4 and 10 power 4. Then what we do is we randomly pick a value. We randomly pick values in the given interval. We randomly pick the values in the given interval and we try them, right? As the name suggests, it's literally random. You're going to search for hyperparameters randomly, which means if these are your values of lambda and these are your cross-validation error, and if I know that the values lie between 10 power minus 4 and 10 power 4, I will randomly pick a bunch of points here. I'll randomly pick a bunch of points. For every point, I'll compute what is the cross-validation error and I'll get a plot. And amongst the random values, whichever value has the best error, has the lowest error, I'll basically pick that as my value, right? That's what the random search means. There is some very interesting literature which shows that random search is almost as good as grid search, or even sometimes faster than grid search, especially when number of hyperparameters is large. Which often, again, the random search concept came from deep learning, which is a very recent area of machine learning, right? So in its entirety, this whole area of trying to find hyperparameters is called hyperparameter search or optimization. There are other complex algorithms like Bayesian approaches to do it, but typically the two broad approaches which are extensively used are grid search, as we explained, with some exponentiation, right? Like 10 power minus 4, 10 power minus 3, 10 power minus 2, so on. This type of approach, or they just do a simple random search. Actually, you can find both of them implemented in scikit-learn. In scikit-learn, both of them are implemented, right? So for example, if I go to this page on scikit-learn, so it's called grid search. This page is called grid search. on scikit-learn. So you have two types of grids. You have two very popular grid searches that are available. You have something called as grid search cross-validation, right? Which does what it says. It tries to do a hyperparameter optimization using grid search. Similarly, you have random search cross-validation, which is again a function which helps you do cross-validation search for hyperparameters like lambda, right? So by the way, this need not be used only for logistic regression. This can be used for k-nearest neighbor. It can be used for Laplace smoothing, right? For any hyperparameter, the typical standard process or the typical standard techniques that are used are grid search cross-validation and randomized search cross-validation. And there's a lot of code documentation available here in scikit-learn's documentation for you to easily understand how to do it, right?